Hello, I'm Nat Karmios, and this is the Gillian-C demo, where I'm going to apply our C memory model to some of the previous while exercises and verify some real-world C code. As you'll understand, C is a much more nuanced language than while, and this means we're going to see a more complicated side to Gillian, so buckle up. Let's get started with a familiar example, list length. Instead of using unstructured heap cells like you saw in while, we're using the natural choice to C, a struct. Here we have a list node struct with the data stored in the node and a pointer to the next node. Peeking under the hood at the intermediate code, we see Gillian has created a predicate for our struct. Now, we use this predicate at the source level with this points to syntax, like you can see in the list predicate here. For posterity, the M here means that the memory is mallocked and it can be freed. Now, this predicate is largely the same as what you saw with while, with an additional constraint on the size of the list, which will become relevant in a moment. The function is also very similar, with an identical pre and post condition. Now, verification looks much the same as well, with branches for the empty and non-empty cases and a recursive call. Now, the heap looks a little bit different to what you've seen in WSDL. We can see the list node represented with the data at offset 0 to 4. We see this alpha 11. This is the first element of alpha. A hole between offsets 4 and 8. This is uninitialized or undefined or poisoned memory, which we're not allowed to read. And the tail of the pointer between offsets 8 and 16, represented logically by a list of location and offset. Don't worry about this negative offset here. This is some legacy behavior related to the concert memory model that Gillian-C is based on. Now, we can see an error in the non-empty case. We haven't made any glaring mistakes in our code this time, so what's going on? Well, it tells us that the length of this variable, let's check our state. Okay, alpha16 is the tail of alpha, so the tail of alpha may not be between these two numbers. Now, you may know these numbers to be the minimum and maximum values of a signed 32-bit integer, the int type, in C. A key difference between while and C is the additional concern of integer overflow. Here, there could be more list elements than the int type can represent. The list predicate shows this by restricting the length of the bounds of size t. Therefore, quite subtly, we need to change the return value of the function to size t. And now our function verifies. Now let's turn things up a notch with some collection C examples. So this data structure and the associated functions are in fact taken from the real-world collection C library. You've previously seen it adapted to while, but this code is largely the same as what's in the real library today. Alongside our existing list node struct, we have an outer list structure with the size of the list and pointers to the first and last nodes respectively. Now here is the familiar list segment predicate and predicates for the outer list structure. We have this outer predicate ensuring that memory is in place for the outer list structure, and an inner predicate that reasons about the contents of the list. Similar to the while examples, we have some lemmas for reasoning about list segments, one for appending to a list segment and one for concatenating two list segments together. Now we'll start with add last, the equivalent of list append, where we take a lister x and a value v and ensure that v is appended to list at the end. The program starts by allocating a new node and storing v in it. Then, if the list is empty, we point both the head and the tail of x to the new node, forming a singleton list. Otherwise, we point the final element of the list to the new node and update the tail pointer, thus extending the list. And in both cases, we increment the size of x. When we start debugging, you'll notice that verification is already branched. As an optimization, Gillian will sometimes unfold predicates that appear in function specs and other predicate definitions when pre-processing the program. Here, we end up with two cases corresponding to whether alpha is non-empty in the left case here, or empty in the right case. Let's look at the empty case first. This is a good opportunity to see the memory model in action as we allocate memory for the new list node. After calling calloc, we have a new memory location with known bounds and the contents set to 0. Once again, ignore this negative offset. Notice that we have zeros instead of uninitialized or undefined or poisoned memory because we use calloc rather than malloc, as this initializes memory to 0 for us. Now, notice how after we assign v to the data field, this offset range between 0 and 16 is further broken down into the range of 0 to 4, which stores v that we've just stored, and 4 to 16, which remain as 0. And we can illustrate that this is a valid list node by folding. We can see that each memory cell, shown by these mem single assertions, are consumed, along with the hole that ensures alignment and the block's bounds. The rest of the empty case succeeds trivially. But we have a problem in the non-empty case. We can't match the post condition. So matching tells us that we can't be sure that this logical variable, alvar35, so let's see, 1 plus the length of alpha. So we can't be sure that 1 plus the length of alpha is less than or equal to this number. Integer bounds are rearing their head once again. The subtle part is that we're checking the length of alpha plus 1 because we're adding an element to the list. So let's add that constraint to our precondition. This branch is still failing. So looking at the match once again, down the bottom here, we see that we have the SLL predicate needed in CC-list-HT, but not the lsec. Now let's make things a bit easier on ourselves by giving some names to the things we want to reason about. You might recall that we can add assert tactics, which combine names. Let's split alpha into its last element, AT, and the rest of the elements, AH. Let's also name the initial head and tail pointers of x, xh and xt respectively. Looking at the state now, we see an lseg with AH, an SLL with V, and a loose heap cell with AT. This is where we need to apply lseg append to stitch AT and AH together. And thus we have a verifying function. Finally, let's look at splice, the equivalent of list concat. Here we take two lists and ensure that in the end, the first list contains the contents of both, and the second list is empty. In the trivial case that y is already empty, we don't need to do anything. If x is empty, then we splice in y's contents wholesale by reassigning x's head and tail pointers respectively. Otherwise, we join the lists by pointing the tail of x to the head of y and updating x's tail to be y's tail. In all cases, we update the size of x and ensure that y is empty. Again, we start with a few different branches already. This time we have 4, for each combination of alpha and beta being empty and non-empty. These two cases are trivial, with an empty beta. This case is for an empty alpha and non-empty beta, a little bit longer, but still needs no input from us. And then that leaves us with non-empty alpha and beta. As you've come to expect, we need to worry about integer bounds. This time it's a little more subtle, as we need to make sure that both lists are fully addressable. See how we're adding together the sizes of both x and y. So let's fix the precondition. Now we still have a failing post condition, and this match gets a fair bit hairier than the previous example, as there are more viable predicates for Gillian to try and unfold, even though it still doesn't get to the answer. However, looking at this first matching attempt, we can see this takes much the same shape as the previous example. So let's once again put in a binding assertion to help us out. And here we pick apart both lists simultaneously. Now, this time, not only do we need to join the tail of alpha to its head with lsec append, we also need to join alpha to the head of beta with lsec concat. And at last we have a successful verification. Now, from each of these examples, you can see that, despite needing some guidance in parts, Gillian brings a whole lot of automation to the table, especially compared to hand proofs. It automatically figures out how to match the state against assertions, and it's usually able to juggle the folding and unfolding of predicates for us. This automation is particularly helpful here in real-world C code, where abstracting logic with predicates is key to keeping complex proofs manageable. We welcome you to try out the Gillian lab for yourself. It includes a number of while exercises to ease you into verifying with Gillian, as well as some tougher ones, including real-world C code, that'll put Gillian and your understanding of CSE to the test. See the course webpage for more information.